Hello, this is Dr. Hassan Abdullah with the course Deep Reinforcement Learning. And that course consists of several topics. And one of those topics, important topic, is convolutional neural networks, which is topic number 7. And the subtopic is A, which is the fairly easy concepts. So the lecture is 7A. And this video uses the supplemental website of this course. You can access this at www.ezmcq.com/GoGet, and this is a personalized learning management system. The approach adopted in this course is based upon content delivery, and the features of that content delivery are listed on your screen. And this is ahead of the traditional slides based approach. And this approach is literally used by hundreds of millions of online users throughout the world. And based upon that content delivery, we have developed the personalized learning management system. In green color is the URL of the personalized learning management system, and it consists of several features. The key 6 features are shown and demonstrated in 6 videos. The URL of those videos is shown on the screen in blue color. So, what are those features? For example, full text search in the content of all the questions and answers, and ability to support people having handicap or disability or some limitation of viewing, so they can send or set the color, size of the font, spacing, and so on. And it optimizes the limited space of the smart handheld devices in a hierarchy of the content. And then, of course, you can also track your progress so that you know what you have done and what you need to do. And there is the facility of online testing and grading and evaluation of results. And of course, this is centered around the question and answer based approach, which is engaging, which is thought provoking, which is very powerful, which is proactive also, and the details of the traditional approach. So it's the best of both worlds, and it is a blending of these two technologies and techniques. So in front of you is the list of topics which are covered in this course, and we are at topic number 7. That topic is convolutional neural networks, and the contents of this topic are on your screen now. Every question and answer is a concept. So those concepts are divided into groups. So the lecture number 7A grouping is shown in yellow color, and the next grouping in green color, and so on. So the difficulty from yellow to purple increases progressively. Now, without further ado, now we move on towards the actual lecture. So we start with lecture 7A of deep and reinforcement learning. So what is a CNN, convolutional neural network, first of all, and how does it differ from fully connected networks? I will explain what is meant by a fully connected network, and you will see it also. So the topics which we are looking at, or the subtopics, is the local connectivity. Okay, what is meant by local connectivity, that I will discuss. Then the parameter sharing, which will be clarified using this diagram. And this is like the work with spatial hierarchies. How, I will explain. I'll explain all of it. All right. So this is a fully connected network. If you see, I will explain everything to you. This is a fully connected network because here we have 9 nodes, and here we have 4 nodes. So there are 9 into 4, 36 edges. Okay, so this is a fully connected network. And this is not a CNN. Yeah, this is a CNN. And this is not fully connected. Okay, you can see the number of edges. Of course, the number of the input vector size. So we had an input vector for fully connected. Over here we have the matrix input. I'll explain what is meant by this. Okay, let's go into some details, right? So first of all, neural networks are a set of dependent non-linear functions. Okay, because that's the beauty of neural networks, that it captures the non-linearity. And each individual function consists of a neuron or a receptron. Now try to understand. In fully connected layers, this is fully connected, okay? The neuron applies a linear transformation to the input vector through a weights matrix. This is the input vector, and this is the weights matrix, and this linear transformation results into the output vector. So how is it applied? This is applied through a non-linear activation function f. This is the activation function f, right? So this dot product results in this, right? Now, if we consider an example of a layer in a fully connected neural network, say with the input size of 9 and an output size of 4, the operation can be visualized as is shown here. Okay. So what the activation function does, the function wraps the dot product between the input vector layer and the weights matrix. Now what happens? Now remember that the columns in the weight matrix, each column in the weight matrix would all have different numbers. They will have different numbers, okay, and would be optimized as the model is trained, right? So what is meant by optimizing? You would like to reduce the loss or the error. So this input is a 1 by 9 vector, okay. The weight matrix is a 9 by 4 matrix. So while taking this dot product and applying this non-linear transformation with the activation function, of course, okay, we get the output vector which is 1 by 4, and this is the visualization of the corresponding layer. So this is a fully connected network. So you can see that why we call it fully connected, okay. And the weights of this neuron only affect output A, which is shown in orange color, and do not have any effect on outputs B, C, and D, right? Now let's look at the convolutional layers, okay. So convolution is basically or effectively a sliding dot product. It's not a fixed, it's the sliding dot product where the kernel shifts along the input matrix. I also showed you an animation also. And we take the dot product between the two, between this and this, okay, as if they were vectors. So this is considered as a vector. Then you move this, then you have another vector, you move it, and then you have, this is fixed, this is changing. So you can see that by taking the dot product between the fields in orange, output as a scalar 1 by 4, okay, 1 by 4 into 1 by 1, and sorry, 1 by 4 into 4 by 1 results into a 1 by 1. All right. So this is basically this is the result what I was discussing, and this is the visualization of the convolutional layer. So you can see it's very obvious that convolutions are not densely connected, as we can see in fully connected, and not all nodes affect all output nodes. So there is an advantage to this that makes convolutional layers more flexible in learning. Furthermore, the number of weights per layer is also smaller, of course, which helps a lot with high dimensional inputs such as image data. Now, due to these advantages, we have what are called as CNNs with their well-known characteristics of learning features in the data, such as the shapes and textures in the image data. Okay, so this explains a lot. Now, what is meant by local connectivity? You must have understood it by now. I will talk through this. So CNNs use local connectivity, which we have seen, to link the neurons to specific regions in the input. Okay. So we are looking at specific regions in the input. Okay. And then this captures the localized patterns. This moving thing captures the localized patterns like edges or textures. Now what happens that this design mirrors how visual perception works, right? And it helps reduce the computational complexity also, as compared to fully connected layers. Now remember one thing, that computational complexity also translates into consumption of power. So they consume less power. So what we are talking about, I was talking about this local connectivity. And then is the parameter sharing. So parameter sharing, so we have a single filter in a CNN, which is applied across the entire input. Okay. What does it means is that weights are reused as opposed to a fully connected network. So this reduces the number of parameters, obviously. And when the parameters are reduced, it can improve generalization depending upon the image type. Unlike fully connected FCNs, where each weight is unique, I've shown you that. And because there is a lot of these weights, so they are prone to overfitting. Then are the spatial hierarchies. So CNNs build the understanding layer by layer, layer by layer. Okay, and they detect simple patterns first and gradually recognize more complex structures. So they kind of capture the hierarchy. Now this spatial hierarchy makes CNN ideal for what? For visual data and deep reinforcement learning. How? Because it enables the agents to interpret the visual scenes meaningfully. For example, for this is a building, say for example, then there's the front of the building, then there's the window, then the window pane, and there's a glass in the window pane, and so on. Right? So this is an analogy. Furthermore, just hold on for a sec. I've lost the mouse pointer. So then we have the reduced parameters. By limiting the number of connections because it's not fully connected and reusing the weights, which I showed you, CNNs are far more parameter efficient than fully connected networks. So what it does, it enables the use of deeper architectures. So because when you add more layers, basically you are capturing more detail. And at the same time, since it's not fully connected, you are maintaining the computational feasibility also, which is of course desirable and required and essential for large scale visual processing. All right. So what is meant by translational invariance? CNNs can detect the same feature anywhere in the input due to the shared filters. Now that helps them to be robust to positional shifts. So if you have a picture of a person at different positions, this CNNs can capture those things. This is especially beneficial in tasks where the position of objects changes, such as game frames in reinforcement learning. Okay. So now we move on to the next Q&A. Okay, let me clean this for you. So here are the details, what I talked about, and here are the references also. So the next concept which we are interested in, how do convolutional layers extract spatial features from input data? Now this is explained using these bullets. So they are sliding filters, which is like inherent to uh, convolutional neural networks. Then we will talk about the receptive fields, what is meant by them, because we are looking at a part of it, receptive fields. Each neuron can view small local section, okay, and feature maps, and we will go through all these details. So, what are basically? Let me briefly give an overview, and then we will go through the working of this example over here, and then I'll move to explaining the bullets. Okay, so convolutional layers extract spatial features. These are the convolutional layers. They extract the spatial features from input data like images. This is an image by applying small learnable filters through a sliding window. So instead of the entire picture, there's a sliding window which moves through part of this image. Now each filter, what it does is that it detects patterns such as edges or textures. So this is an edge we are looking at, and there could be textures also which are not visible here. By how they're extracted by a dot product with local input regions, which captures the spatial dependencies, which we have discussed in the previous Q&A, right? So then each neuron has its own receptive field, and which I just mentioned here. Each neuron has its receptive field, right? Has its receptive field that defines the input area it observes. So this entire image is kind of part of the images are defined are assigned to different neurons. Now by adjusting the filter size and the stride, you are able to catch different spatial resolutions as required. So if there are more details in which there is interest, then there is there's certain different filter size and stride, and depending upon, right, so different resolutions are used. Now the resulting feature maps highlight where features appear, which are of interest and are passed through non-linear activation like the ReLU to learn complex patterns. Now, when you stack the layers, okay, when you stack the layers, that enables the hierarchical learning. Okay, now what is part of what? Now, the layers in the beginning, the early layers, okay, they detect simple patterns, and then of course we have deeper layers capture more complex shapes or objects. Now, there is a progressive abstraction that makes CNN highly effective for tasks like image classification or object detection or reinforcement learning, where there's a need to visually structure. Now, let's look at this figure. This figure explains the procedure of CNN. So, suppose that we have an image of size 28 by 20 by 28. Okay, we have that image 28 by 28, and through a 5 by 5 kernel, right? The input image is perceived by several feature maps, okay, that results into 24 by 24 convolutional layers. So these are the 24 by 24 convolution layers. Now, convolution extraction is basically preceded by the neural activation function. What are neural activation functions? That we covered in the topic in neural networks. Now, these nodes are overlapped as same sizes of nodes. Okay, same sizes of nodes. The capacity of convolution layers has to be reduced or lessened. Now, to reduce some convolution layers, there is a polling layer, okay, and for subsampling. Now, this polling also gives the input image correction. So that's not part of this course. It's so much detail. But what we can see is that as the polling works, as per proportional rate of pixel, it consists of 12 by 12 polling layers. So we had from 28 by 28 image, we reduced to 24 by 24 convolution layer, and then we reduced to 12 by 12 polling layer. Now, these convolutions and polling methods proceed one part of the global feature. Now, recognize that the prior feature maps are preceded again as feature extraction, and we end up with 8 by 8 convolution layer. Then we perform further subsampling, okay, through a 4 by 4 polling layer, okay. And last feature maps consist of 1 by 1 input that fully connects the layer. 1 by 1 input that fully connects the layer. Now, this output is expressed by means of one of the classes. So that's how it works. So the details are given here. So I would suggest that you go over the details. All right. So what is meant by the sliding filters? Now, filters move across the input data and compute the dot products. Okay. Highlighting, and what it does, it highlights patterns like edges, which I showed you in the previous Q&A, not the previous one, but in the topic 6D, I believe, of deep reinforcement learning. So what this does, this method allows spatial feature detection regardless of the position, right? Making it efficient for visual tasks. Good, that is nice. Then the receptive fields. Now, each neuron looks at a specific part of the input. So more neurons, you can look at more details, but that will require more hardware and more computation power, more energy, and more accuracy. As layers deepen, receptive fields grow. As you go further, because the first layer has certain detail, the next has more detail, and so on. So as the layers deepen, receptive fields grow, enabling detection of more complex and large-scale patterns. Right? It's like kind of a zooming. That's an analogy, okay? So feature maps. So these are the outputs of filters, and that indicate where the features occur in the input. Now, there can be multiple maps. There are multiple maps from different filters, and what they do is they help capture diverse aspects of the data. And then are the activation functions. So what are activation functions? Functions like ReLU and non-linearity after convolution. Now, what this does is that this step enables learning of complex patterns. How? By keeping only the meaningful. What is meaningful? Positive activations in the output. So keeping track of where activity has happened. And finally is the hierarchical learning. Hierarchical learning. Now, since there are successive layers of CNNs, they learn increasingly complex features from simple edges to full objects, right? Now, what this does, this helps in forming a rich and structured understanding of the visual data, right? So this is what we have discussed, and that's all it is for 7. This is like we are still going with 7 here, as a matter of fact. So we look at the polling and activation functions. So what roles do polling and activation functions play in CNNs? Because we looked at them in the previous concept also. Basically, what they do is they reduce the dimensionality. So dimensionality reduction reduces the complexity of the problem, of course, the processing cycles and energy also. And it also generalizes the features. Instead of specific ones, we have generalized features. And it introduces the non-linearity. So as I mentioned earlier, this results in efficient computation. And so if you look at the detail here, the detail which we will be discussing, right? And before we go into the discussion, let's briefly talk about how they interact, polling and the activation functions. So in convolutional neural networks, polling and activation functions play a crucial but distinct roles in learning. So what polling layers do is that they reduce the spatial size of the feature map. As you can see, they reduce the spatial size of the feature map, which is 4 by 4 into 2 by 2. And the techniques used are like max or average polling. This is the max polling and average polling. So what it does, it lowers the computation and parameters while retaining the important features. So details are gone, will reduce, obviously, but important features are retained. And this introduces translational invariance. What it does is that it makes the models more robust to small input shift because these small relationships are gone. Okay, so this entire gets replaced by this. Now, furthermore, activation functions add non-linearity. So with the non-linearity added, CNNs learn complex patterns because the non-linearity, because otherwise they would just miss the variations, okay, and would just lose everything. So without these activation functions, even deep networks act like linear model. So and that linearity is useless because the life is highly non-linear. So functions such as ReLU are commonly used. Why? Because they're efficient and they help in avoiding the vanishing gradients, right? Which you can encounter in saddle area, saddle points. So when we combine the combined pooling simplifies feature map of robust generalization. This is more robust than this one. And activations allow deeper models to learn non-linearly, learn abstract representations. So as a consequence, CNNs are effective for image recognition, natural language processing, and deep reinforcing learning tasks. So what is dimensionality reduction and how it goes about? Polling layers reduce the size of feature maps, which we have seen, lowering computation and memory costs, of course, but there's a certain cost also. So as a result, training gets speed up and the network becomes scalable for larger data sets or inputs. Feature generalization. Polling reduces the features, it kind of dampens the features. So polling allows CNNs to focus on the most important features because of the average and the max, while ignoring irrelevant spatial details. So as a result, the model's ability to generalize across varied inputs is enhanced. So that is feature generalization. Then is introduction of the non-linearity. Now there are different activation functions which we have covered before. So activation functions like ReLU make CNNs capable of learning complex patterns by the introduction of the non-linearity. And that non-linearity is essential for deep learning because in real life we have more of a non-linear environment and relationships. Efficient computation is linked with dimensionality reduction, which I've explained before. Robust enhancement. Pooling and activation together, pooling and activation make the model less sensitive to minor input changes. All right, let me move this for you. Minor input changes, improving performance on noisy data or distorted data while maintaining the key feature recognition. So here you can see I've discussed before. So this is the max pool. So the max of this group is 9. The max of this is 7. So these details are gone. 2 and 2 and 1. These details are gone, right? Over here it's the average poll, but of course there is many other issues here. So this average, the impact of this 1 is almost negligible. Impact of 3 is also negligible. All right. Impact of 2 is negligible. 1 is also negligible. So we can see that these max pool and average pool, they let go of these details, okay, and these distortions small also. So that's their benefit.